First, I would like to thank Diogo and the IPAM team for creating this opportunity to meet. This talk is my joint work with Xuwei Yang. It's about mean field Stackelberg games. Here is the outline of this talk. At the beginning, I will give a little bit background about the major player model. And the next part is about the limiting decision problem for the Stackelberg game. Here in this model, we have two players in the picture in the end. So that is, we have a leader and a representative minor player as the follow. This is from an infinite population. To propose a solution to this problem, we will actually use dynamic programming, and this is based on a notion called t-selves. And the last part is for the LQ case. We will use this kind of LQ models to illustrate the feasibility of the dynamic programming approach. So to begin with, let's have a look at the system model. We actually have two parts. First, we have the dynamics, and the next part is about the control objective, that is the costs. So let's check what kind of agents we have. In this model, we actually have n+1 players. So here we use A0 to denote the major player, and the AI to denote the minor player. So we have two state processes. Actually for the second part, we have n processes for the minor players. In the model, T super K is for the state of the individual players. We have the control UTK, and then the independent Brownian motions in the SDEs. Here, this mu super n is used to denote the empirical distribution generated by all the minor players. And we also have a little bit assumption about the initial states. So here, let's check what's the difference between the major player and the minor player. We can actually look at the equation of the minor player. You can see in the SDE of this minor player, you have the state of the major player, and also its control. That means the major player has significant impact on each minor player. And for this reason, we have the name of the major player. But if you have a look at the minor players, you can see each minor player only receives a very small impact of another minor player through this empirical distribution. So for this reason, they are called the minor players. So this is the dynamics. We can give a little bit motivation for this kind of modeling. You can thinking of, say, in our financial market, you have a very big institutional trader, and then you have a very big group of individual persons as much smaller traders. So that's a motivating background. And for the next part, we have the costs for the major player. it depends on its own state, then the empirical distribution and its control. Okay, for the minor player, we have its own state, own control, the empirical distribution, then the state and the control of the major player. Okay. And we have a little bit notation. We use U sub minus I to denote the control of all other minor players, okay, except minor player AI. Okay. So this is the dynamics and the cause. Okay, there is already some history about this kind of modeling. Okay, for mean field control, it was initially introduced in an early paper, okay, with a major player and the n minor players. Okay, they do mean field games. Okay, so for this kind of major minor player models, okay, the first set of literature actually considers large equilibrium solutions. Okay, so in this case, also the major player is much bigger. In some sense, all the players somehow are symmetric. Okay, they choose their strategies simultaneously. Okay. So it's a large game situation. Okay. And in the recent work of the two groups, okay, they actually introduced master equations. So it's kind of dynamic programming for the model with a major player and a large population of minor players. Okay, in the end, you get a pair of dynamic programming equations. Okay, instead of just one equation, like it's a master equation in a standard mean field game. Okay, you have only one master equation. Okay, but here you will get a pair. So given this kind of major minor player modeling, there is another optimization framework. That is, you can consider leadership. Okay, that is the leadership of the major player. Okay, in this case, the Stackelberg equilibrium can be studied. Okay, for example, we can check the literature by Wang, Zhang, Van Susan, Moon, Basa, who host, and the paper of Eddie for the principal agent problem. Okay. So here you can see there is already some literature using the solution notion of the Stackelberg equilibrium. Okay. The main issue here is they mostly depend on the maximum principle on a fixed time horizon. Okay. Then the limitation is that there is no time consistency. Okay. If you stick to a fixed time horizon. Okay. That means when you play this game, okay, in the middle, it is possible you come up with a plan which is different from the one solved at the beginning at time 0. Okay, so that's the time consistency issue. Okay, so for this work, our objective is to introduce a different approach, okay, so that we can overcome this trouble, okay, this time inconsistency. Also, for the traditional literature on Stackelberg games, I will mention the starting point by Stackelberg, and also the classic textbook by Bashar and Oyster, and also some recent papers by Yung and Susan. They consider stochastic modeling and the Stackelberg equilibrium characterized by the stochastic maximum principle. Given the minor player model, let me give a little bit notation. Okay, actually, this is the Fourier probability measures with finite second moment. It has been used a lot by other speakers. Okay, we install the Waterston metric in this space. Okay. And also here we denote the set of functions. Okay, it means twice continuously differentiable functions with bounded second derivatives. Okay, so it's a bounded second derivative. And we also have some assumptions for this final player model. The objective here is to ensure we have well-defined state processes and the costs, okay, under such strategies. Okay. So we want to ensure the model makes sense. Okay. In this set of assumptions, we want to allow unbounded control set, okay, so that we can include the IQ case, okay, which we will start at the end. So here, the basic problem is to develop a Stackelberg equilibrium solution of low complexity, okay, and our plan is to formalize a right mean field limit model. Okay, we will then combine a notion of t-selves with dynamic programming. Okay. So in the end, this approach is different from what is done here, mostly through the stochastic maximum principle. Okay. Here I did a bit remark about t-selves. Okay. Actually, there is already some history about this notion. Okay. In an early paper by Ekeland and Lazrak, they adopted this notion for optimal control with time inconsistent cost. Here, for this work, we will formalize a right mean field limit model, okay, and solve it by dynamic programming. As I said earlier, okay, there is an important subject that is error bound estimate. Okay, but here we will not do that. This is actually work in progress. Okay, so let's recall. Okay, a few minutes ago we introduced the dynamics for the agents. Okay, the crucial issue here is how to describe a representative minor player in a very compact manner. Okay, from the equation we can see, okay, each individual minor player is interacting with a huge group of other minor players. Okay, so it's a very complicated interaction. Here, what we need is to find a more compact specification. Okay, but we need to do a little bit abstraction, and we do that by mean field approximations. Okay, so let's check what's the the basic idea to proceed. Okay, this idea here is not new for major minor-player models. Okay, it's already widely used in the literature, but it's good to warm up. Okay, first, given a probability distribution mu and the a test function g, okay, from this side, okay, we denote the integral, okay, and the next for the empirical distribution in the actual model, we pi it with a test function. Okay, so in the end you get a number. Okay, this is actually a random variable. Okay, after you calculate the integral here, then we apply Ito's formula. Okay, do a little bit calculation. In the end, you get this end product. Okay, intuitively, when n is big, okay, the very last term will disappear. Okay, because of the law of large numbers. Okay, that means actually we only have the leading term surviving when n is going to infinity. Okay. So this suggests we can introduce the limiting dynamics. Okay, and we can write it in this form. Okay, it's actually called an ODE in a weak form. Okay, we take this function g as a test function. Okay, for the limiting distribution. So it's very neat. Okay, the interesting feature here is for this ODE in a weak form, we actually have a driving force from the major player. Okay, so this is the state of the major player, and at this moment, for simplicity, we suppose U0 and the U here are just two constant vectors. Okay, we do not consider control strategies yet, okay, at this point, just to make things simple. Okay. And indeed, if we want to replace the constant vector here by a control law, then we need to modify the interpretation a little bit. Okay, so this is about the extension to feedback. Okay, in place of the control vectors, okay, in place of the constant control vectors. Okay, here let me use some simple examples to illustrate. Okay, the first is a trivial case. The major player has no effect on the distribution, okay, which is used to describe the mean field behavior. Okay, in this case, the drift of the major player is actually equal to a function like this. Okay, only its own state than the mean field. Okay, so there is no impact from the state of the major player. Okay, in this case, this ODE in a weak form actually becomes the FPK equation of an underlying Minyi-Huang SDE. Okay. So this is the trivial case. In the previous part, okay, basically we mentioned how to do a little bit model aggregation, okay, so that you can summarize the impact of the mean field, okay, according to a very simple equation. Okay, so now let's try to put these three equations together. Okay, we have the SDE of this major player and the SDE of the minor player. At this point, we have already replaced the actual empirical distribution by this limiting object. Okay, recall that in the actual model we have the empirical distribution. Okay, so now we replace it by this distribution mu s. Okay. For simplicity, here we reuse notation. Okay, we still denote the state process by x super zero, okay, for the major player. And similarly for the minor player, we use the limiting distribution mu s. Okay. Then we have the third equation. Here we have a little bit remark about how to understand the model here. Okay, so basically we treat these three entries, okay, as the system state. Okay, so we have the major player's state, the minor player's state, then the distribution mu s. Okay, here mu s is used to drive the evolution of the two random processes. Okay, actually we have a specific requirement in order for this mu s to make sense. That is, this mu s is also regenerated from the empirical distribution of infinite minor players. Okay, in general, we have neither mu s equal to the law of the minor player, now mu s equal to the conditional law. Why? The reason is that here we have an arbitrary choice of x1. Okay, so we have the freedom to choose any x1, and also for the mean field measure flow, okay, we can arbitrarily assign the initial condition. Okay, so so this xt1 almost has nothing to do with this view. Okay, for this reason, we do not expect to have the equality property, okay, either this version or the second version. Okay, this is a little bit different from the treatment of the mean field in the literature when other people dealt with major players. Okay, they very often use conditional distributions. Okay, here we will not do that. And also another note, the third equation essentially results from the second one. Okay, but it's informative to list it separately. Okay, so here why we can say the third equation essentially results from the second one. The reason is that here you can use the second equation, okay, to regenerate different particles with independent Brownian motions, okay, and the different initial state selection. Okay, in the end, you check the empirical distribution, and then let the number of particles go to infinity. Okay, in the end, by this procedure, you will really get an ODE as given by the third equation. Okay, that's why we can say the third equation essentially results from the second one. Okay, as long as here we impose some special requirement on this measure flow, okay, for the mean field. Okay, so at this point, we use the entry US0, okay, and U1 US1. They are interpret as strategies. Okay, so it means we want to look for some kind of feedback based on the system state here. Okay, this should be mu sub s, okay, because s is the is for time. Okay, t is selected as the initial time. So now the big question is how we can eventually work out the feedback strategies, okay, in terms of this kind of extended state space. Okay, the state space is extended by adding the mean field here. Okay, in the mean field Stackelberg here, Stackelberg game here, we let A0 be the leader. Okay. So that's the aggregation of the system dynamics. Okay, so that in the end we have the mean field measure flow. Okay, driven the SDEs. Okay, we just have two SDEs. Okay. Similarly, in the two curves for the major player and the minor player, we use the mean field measure flow. Okay, so in the end, in the picture, we just have two players, the major player and the minor player. Let me give another example to illustrate how this kind of modeling works. Yes, we consider linear model. So the drift of the major player is given in this form. Okay, it has its own state for the major player, and the second term is actually the mean determined by the measure mu. Okay, it's the first moment of mu. Okay. Here, z is a vector. Okay. And for the minor player, we have the state of the major player and its own state, then the average from the mean field mu. Okay. We also introduce the short notation giving the variable z as a vector we can integrate with respect to mu. Okay. In the end, for the major player, he or she will see two related processes. Okay. The first is its own SDE. The second is actually a random ODE. Okay. Why it's random? Because it's driven by the state of the major player. Okay. So given the initial condition here, we can then uniquely solve the equation system. Okay. So this is the illustration of the dynamics. Okay, when we have the linear model here. Some further remark. Okay, given the dynamic characterization of the two agents, the major player and the minor player. Here, we have no constraint on the choice of the initial state at the initial time t. Okay, for the minor player. Okay, you can that means you can set any initial condition. Okay, it has complete freedom. We need to do this. The reason is that in the end, we want to apply dynamic programming. Okay, as many of you know, okay, when we use dynamic programming to solve stochastic control problems, okay, we want to check all possible initial paths for the initial time and the initial state vector. And in the end, however, if we want to do performance analysis, in the end, we will need some restriction about the initialization of the minor players. Okay, that is, the initial empirical distribution should match the initial choice for the measure flow. And also for general nonlinear system here, we have the existence question. Okay, actually, to give a complete answer to this question, it is still a little bit too early. The reason is that the answer of this kind of questions depends a lot on the structure of the control laws. Okay, in any case, given the compact specification of the dynamics here, we can formally proceed to do dynamic programming. Okay, that's actually the basic idea of master equations. Okay, so now let's check how dynamic programming works for our model here. The idea is here. First, we consider state feedback. Okay, and for the major player, he or she would see a state including its own state and the mean field. Okay, for the minor player, its word consists of the major player's state, its own state, and the mean field. Okay, if we use I to index the minor player. Okay, and next we introduce a notion of t-selves. Okay, following the practice of Ekeland and his quasar. Okay, so the idea is here. Basically, we have two short-lived agents. Okay, the major player, the minor player. Okay, at the end of t plus epsilon, they both die. Okay, for the future, it will be taken over by other players. Okay, the conceptual point is that at a different time t, okay, even this is one person called major player, you actually interpret as different t-selves. Okay, we can think of this. Say today, Chen is chairing the workshop. Okay, so Chen will work for will do the management of the sessions for Wednesday. Okay, after the end of today, Chen retires. Okay, tomorrow it will be taken over by another guy, but Chen will actually care about the quality of the workshop for Wednesday till Thursday and Friday, okay, until the end of this workshop. Okay, we can do another comparison. Okay, thinking of a good-hearted father. Okay, the father will only live for his own generation. Okay, but actually for the father's management or optimization, okay, he cares about all generations in the future for the whole family. Okay, we can make a comparison like that. Okay, so given this notion of t-selves, we can now actually merge that notion into our notation. Okay, for the major player, we can now index by different time t. We get t(A0) agent. For the minor player, we get t(A1) agent. Okay, for each agent, we can define the value function. Okay, so now the value function is determined by the initial condition. Okay, for the major player, and also the equilibrium strategies. Okay, this is the Stackelberg equilibrium strategies. Okay, similarly, for the minor player, we have the determination of the value function. Okay, evaluated at the equilibrium strategies. Okay, so the big question is how to determine the Stackelberg strategies. Okay, actually, we will adapt some idea in the literature. This is the textbook by Professor Bashar and his co-author. This approach was actually introduced much earlier in the 80s by Professor Bashar and another co-author. I got the name blockage. Anyway, we can follow similar state feedback information to do dynamic programming. Okay, but here we need to take care of the mean field component. Okay. Okay, so to describe dynamic programming, let's do something quite standard. That is the generators. Okay, so basically here we have the diffusion processes for the major player and the minor player. The first is actually the generator regarding the evolution of the state of the major player. Okay, for the second, it's about the evolution of the state of the minor player. Okay, the last one is about the dynamics of the mean field. Okay, here we have the additional variable y. It's actually used to describe the behavior of other agents. Okay, so here let me first give the end product from our procedure. Okay, so basically we get a pair of HJB equations. Okay, we can actually call this the master equation because we have the differentiation with respect to the mean field mu. Okay, so the first equation is actually for the value function of the minor player. The second equation is for the major player. Okay, and the a special feature to load. Okay, for the generator L sub MF, actually it acts on the y variable. Okay, so we use the red letter to highlight. Okay, to get the two equations, even if just formally, we need a big assumption. Okay, that is the value function is good enough. Okay, having good regularities. Okay, in the end, we can get the two HJB equations. Okay, actually, we can compile the equation system with the standard master equations. Okay, in this case, for a standard mean field game, you just have a single master equation. Okay? But now, because you have the major player and the minor player, you will have two equations. So a brief note about our method. Okay? As I said, we use the notion of t-selves. Okay? Actually, in order for the idea of dynamic programming to work, actually we consider a small collision. Okay, that's like a very small group of players with the size of epsilon. Okay, we expand the value function. Okay, first we write the value function in the additive form. Okay, this is the running cost with time window epsilon. Then this is the future value function with a little bit of discount here. Okay, then just do Taylor expansion. Okay, so formally we can derive the dynamic programming equation. Okay. And here we will give a little bit detail about the choice of the optimizers. Okay, that's actually the most important part of this talk. Okay, so first we are given the action of the major player. We choose the best response of a representative minor player at this point denoted by U height super 1, okay, because this is for A1. Actually, this minor player will try to maximize H1 by choosing its U1. Okay, the trick here is that also U1 appears in this mean field structure. Okay, we should protect this part. Okay, this is the forbidden territory. Okay, this minor player should not touch it. Okay, it optimizes the U1 here appearing on the first line. Okay, here we have a little bit discussion why you should protect this part. The reason is that this mean field is generated by all other minor players. Okay, the minor player in question cannot affect the dynamics of all other players. Okay, that's why you should protect this part. And then we continue to update the strategy of the major player. Okay, given the choice of the optimizer of the minor player, then the major player try to optimize. In the end, it gets something depending on the state, mean field, and so on. After this, we plug in this mu0 start term into the minor player's initial strategy you hide. Okay, so it's updated into this feedback form. Okay, remember that this mu0 start term is already given as a function of the state. Okay, so we can summarize the above procedure to get the workflow. Okay, given the major player's initial choice of action, we get the best response of this minor player. Then the major player finalizes its choice of action, and finally, the minor player decide its strategy. Okay, we also have a little bit discussion why this can be explicitly computed when we have nonlinear dynamics and costs. So this is the most confusing part about the choice of the optimizers. Okay, because of time constraint, I will only roughly mention the LQ case for illustration. Okay, so for the dynamic programming part, after we finish the procedure, essentially we will get the closed loop dynamics. Okay, finally, to illustrate the previous approach, we check how to apply it to an LQ model. Okay, in this case, we have the drift for the major player. Okay, it's linear, and this is actually the mean for the mean field term. Okay, we do average. Similarly, for the minor player, we have the linear dynamics, and also we have the costs given by this kind of a quadratic function. Okay, here we have a little bit of notation. When we use this norm with the matrix in the subscript, it means a quadratic form, okay, with the weight matrix Q0. Okay, so given the linear quadratic model here, we can actually implement the previous optimizer selection. Okay, so we get this Stackelberg equilibrium strategy in this form. Here we denote the value function by V0 and the V1, like what we did previously. Okay, and then we can further write down the two HGB equations. Notice that on the previous page, we have already selected the two optimizers, okay, in terms of the two value functions. Okay, so indeed, we just get the equation system purely according to the value functions. Okay. And next, we try the ansatz for the two value functions. Okay, and here we have the coefficient matrices. In the end, we can actually have 9 matrix unknowns, okay, plus plus a scalar function. So given the guess of the value function, we can write the feedback strategy in this form. Okay, and in the end, after a little bit of work, we can actually solve the unknown matrix functions according to Riccati equations. Okay, actually, we have 9 Riccati equations. It's a lot of terms, but the good news is that it's explicitly solvable. Okay, so here let me summarize the
4 minutes disconnection. Yes.
Yeah, sure. So we have the linear feedback in terms of the state and the mean field average. Okay, so if the Riccati OD system has a solution on the interval, then we have the strategies, okay, as a feedback Stackelberg equilibrium. Okay, also we can show a further property about our strategy. Okay, that's time consistency. So basically, if you have time consistent strategies, it means if you implement the old strategy on the remaining time horizon, there is no need to revise. Okay, it's still an equilibrium strategy for the remaining period or for the subgain. So if the OD system has a solution on the interval, then the set of strategies is time consistent. Okay. So similarly, the previous approach can be applied to discrete time problems. Okay. Again, we can use the Riccati equation and the Dylan programming to solve the discrete case. So here we have a numerical illustration of the continuous time Riccati equation. Okay, so basically, if you can solve the Riccati equation, you can implement the equilibrium strategies. Okay. So to conclude, in this talk, we start mean field Stackelberg games and apply Dylan programming, okay, and we obtain explicit solutions in a few models. For future work, it will be of interest to do performance estimates when we apply the strategies obtained here to a finite population model. Thank you for your attention.